476 is really good class. I was taking, was it Michael O'Connor that was taking topology and then going to 476? One of those guys was taking 376 is the difference. 376 is like going to the circus. It's fun.
He's in my class as well. Michael.
Yeah. So he likes all these prefronting classes. He's probably dropping out of 476 and going, this is like easy, this is fun. All right, so the reason I mentioned the OR major is because these are OR theorems. So the first one is that if you have a continuous function, so this is called the boundedness theorem. And I just put a little note to myself. It's so powerful. You have no idea how powerful this thing is. This theorem is actually used to show uniqueness of solutions for differential equations. It's used to show for PDEs, like you have an extension to multi-dimensions of this guy, and you can show like things about your solution. If you know something happens at the boundary, then you can say everything about that PDE on the inside. Green's theorem, Stokes' theorem, all use this boundedness theorem. It all relies on it. And most of OR, the operations research classes, like the optimization classes, use this theorem too. Did you guys take any OR classes, like nonlinear optimization or linear optimization? So on those classes, you always have this feasible region where you have a function over that feasible region, and you want to find maxes and mins or optimal points in that feasible region. So it can happen either on boundary or at a critical point. That is all relying on this theorem. So even though like theorem seems like, yeah, whatever, they all seem like that until you see it being used, like, wow, this is really a powerful theorem. So suppose I have a closed and bounded interval. Oh, and I didn't mention, these are all used in numerical analysis too. So your bisection method all comes from this. Rolle's theorem, mean value theorem, they all come from this. They are all relying on this. The big other big theorems in calculus. So in calculus, when you get stuff like this, you're really looking for you spend a lot of time in calculus using the tools you built, like taking derivatives, you have all that stuff, and you're using them to find maxes and mins. So those are not just continuous functions, but they're differentiable functions. And when you have that, there's a section in the calc book where you do all the curve sketching first, and then you find optimal points, relative maxes and mins. Do you remember all this stuff, like bringing back memory? Some memories. And then there's this one section where you have a function on a closed interval. And you're supposed to find the optimal points on that closed interval. And it's just one 10-minute section to cover, I think, in a calc class. Don't spend too much time on it. Those of you who did well at the other parts do well at that part. And you're supposed to make a little table where you take the critical points, you find the derivative where it's equal to 0, you find the y values at those critical points, and then you find the y values at the end points. That's your feasible region. Your feasible region is the interval a to b. It can either happen at a critical point inside the max or min, it can happen at a critical point inside that interval, or it's going to happen on the boundary of that feasible region. That was your introduction to OR right there, optimization. And we don't spend that much time on it, but it's like a really important section of the calc textbook. And that's why the students don't like when a mathematician teaches those courses, because they get really excited by that top part. And it's more of a methods course, right? You're just learning how to do things rather than the why this is so important and why this is beautiful. All right, so we're going to show this by contradiction. I mean me. So I'm going to assume on the contrary that F is not bounded. Hence the in-class assignment I gave you just now to come up with a definition because I'm going to use it. Left. One of the things Bartle I think does pretty well. So the proof is in Bartle too. But if F is not bounded on I, by the definitions you just put on the board, I can find, like I can take a sequence n for every n. That's why I had to do this definition thing on the board, so you can get a feel for what that looks like. It's like you put a limbo bar up, n equals 1. According to the definition you have up on the board, it means that you can go above that n equals 1. There's going to be an x value that carries you above that n equals 1. Then you choose n equals 2. You raise that limbo bar. But you know, according to the definition you just wrote up on the board, there's got to be an x value so that I'm above that second limbo bar. Third, so I continue on in this way and I can generate a sequence. They might all be the same x, right? It shouldn't be all the same x because then it'll be a vertical asymptote. But I can just keep raising this limbo bar every single time and find an x value that jumps over that limbo bar, right? So that's what's going on here. What do you feel is going to happen? What theorem do you think I'm going to use? Where do these xn's all belong? Where do they come from? Where do they live? Look up here. Where does your F, what's your domain? And they live in I. So what does that mean about your xn's? Are they like scattered all over the real line? So they're inside this I. So what does that mean about your xn's? They're bounded, which means there's a theorem you can use that takes bounded sequences and tells you something about them. That's right, Bolzano-Weierstrass. Remember when we had Bolzano-Weierstrass? You're like, oh, that's like the trivial theorem. But here we go, using it. Okay, so since xn belongs to I for all n, xn's bounded. Therefore, xn has an invertible subsequence by Bolzano-Weierstrass, or the Baltimore-Washington Parkway. So I can stand for that too. And now I have not used one of my no's. I've used the fact that I'm in a closed bounded interval. I've used the fact that my function's real valued. I used my contradiction assumption. What assumption haven't I used yet? It's continuous. I've got a convergent sequence and the function's continuous. What does that mean? Dr. T's favorite definition of continuity. I told you how much I love this criterion instead of using the definition of continuity.
No, I just saw it. The sequence criterion.
The sequence criterion.
Because the last thing I mentioned, the word criterion, I made such a big fuss with the fact that I like the word criterion. That's what we did in coding criterion. That's why I didn't know that.
Sequence criterion, definition of continuity. By continuity, I know f of x and k has to converge to f of x. And x belongs to I, right? Because we can use squeeze theorem to put that into a little mini proof inside there. But if all the x and k's are inside I, and it's bounded by a and b with a less than or equals, then the limit also has to be inside I. So I know that x has to be inside I. Therefore, f of x, what do we know about f of x? I assumed it's not bounded. So I know this f of x and k has got to be bigger than nk. That's how I created it. But that's impossible. How can it converge to an f of x inside f of, like the f of I range, but be unbounded? That can't happen. That's impossible. You can't have a convergent sequence also be unbounded. The y values form a convergent sequence. And since they're convergent, they have to be bounded.
Then how do we know that f of x and k is greater than nk?
That's how I generated this sequence above, right?
Oh, okay, with f of x.
It should be f of n right there, subscript, right? I didn't add the subscript. All right, so that's my contradiction. So my assumption was false. And the opposite of that assumption is true, which means that f of x is bounded. All right, two more definitions, and then I will have you generate examples. Actually, I'll give you one definition, and then the other one's analogous. We use this all the time, actually, especially with the data that we get today. We actually have continuous glucose monitors now that we've bought. They're not really continuous, but they collect glucose concentrations in the human body every 5 minutes or so, every 5 minutes. And you can generate a curve from that. What I know about those curves is if I interpolate them, the polynomial, they're going to have maxes and mins and critical, like I can use calculus. And so one of the things that we're doing in our group is that, in NPH, is that we're using calculus. When I first saw the group using, what they do typically is they look at area under the curve. And I'm like, that's part of 104, but we got a whole class where we're doing stuff with curves, that's called calculus. So we have total number of critical points you could grab. You could grab absolute maxes, absolute mins. So I kept using the word absolute max. And everybody's asking me in the group, like, what is that? Like, like the absolute max from calculus. Went out, they took the class and forgot it. But it's actually super important. And so the formal definition of absolute max, and absolute min, is up here. These points are actually really important for the kind of data that we have in the nutrition for precision health, because if you think of like when you eat, your glucose concentrations go up, and where it peaks at, you don't want that peak to be too far away from your fasting glucose. The further it's away, it's like having a fever. It's a signal that something's not right. And diabetics have peaks that go way, way high. So you want to actually calculate this absolute max from these curves after you eat something and show that it's not too far away. Or if it is too far away, there's something going on that's maybe not good. So they're important for applications. If you take optimization classes, you know that they're important there. And for everything that's important, you need the definition. That's where we start from. And I'm not going to write up the definition of absolute min. It's just a star, like there's 1 point. The minimum's the exact reverse. Right? The inequality is just reversed.
Right.
So we're headed towards a theorem that says that if you have a continuous function on a closed and bounded interval, then it's going to have its absolute max and absolute min within that interval, or at the end. That's where we're headed. So I would like you to generate some examples first. So that's what the next part of the in-class assignment is about. So think about like what this might look like.
Did that